Okay, so we're ready to start. Today we have Bob Coecke that will be talking about quantum linguistics to space-time linguistics and cognition. Bob has recently moved from the University of Oxford to the private sector, where he's the chief scientist of Cambridge Quantum Computing. I think he will tell us all about it. And Bob, if you're ready.
Yeah, I'm ready. So yes, thanks for having me speaking here. So yeah, I mean, I was part of the QISS network from the start as representing University of Oxford, but like Mario says, meanwhile, I moved to Cambridge Quantum Computing, and more recently, after I joined, we kind of merged with Honeywell Quantum Solutions. So now we are like a bit of a monster in quantum computing with 340 people. So I'm the head scientist. But I'm actually, well, it says Cambridge, I'm actually still in Oxford. So I've got my local team here in Oxford. Oops. I've got my local team here in Oxford. So we started building a new year, and soon will be 30 people. I think a few people you may recognize. For example, Anna, who talked in December a few months ago. She is now working with us too. And also, I'm sure some people here recognize some other faces. Lots of people seem to be leaving academia these days, especially in quantum sector. So I'm going to talk about language first. And I'm going to tell this in a sort of historical fashion. So around 2008, at Oxford University, there were 3 people. So I'll start introducing one. One person was Mernousha Drzadeh. She's now at UCL, and she knew something which I will refer to grammar algebra. She was kind of a logician from background, and she knew grammar algebra. So what is grammar algebra? Grammar algebra is something you probably may associate with names like Chomsky, but okay, I don't know. But the real mathematical brain behind all that stuff is somebody called Jim Lambeck. He came out with this paper in '56, which is the mathematics of sentence structure. And basically the way this works is it's kind of a mathematical system which allows you to verify whether when you stick a bunch of words together, whether they make a well-formed whole, a phrase or a sentence or something like that. So that's this. So that's really what this grammar algebra is. Don't know why it's so dark. Okay. Now, how does this work? I'm going to give a very sort of naive presentation. The best intuition you can have is that of a group. So it's some sort. There are different variations on the same theme. What I'm going to talk about here is some sort of weakening of the notion of a group. So basically, what you got is something which you call primitive types. A primitive type is, for example, a noun. Primitive types are things which sort of make meaningful wholes. So a noun as a word makes a meaningful whole, because sometimes you can be asked a question and then you answer with a noun. So it's a meaningful whole. Another meaningful whole is a sentence, for example. Basically, there are some other things which are not meaningful wholes. And a verb, for example, is not really a meaningful whole. So what you do instead is you build the verb type from a sentence type, but in order to get a sentence, a verb needs an object and a subject in the case of a transitive verb. So the way you indicate that is by putting this noun with a -1 on the left and this noun with a -1 on the right to indicate, I mean, I'm talking about English now specifically, that a sentence needs a noun on the left and a noun on the right in order to form a sentence. Now you see already in which way this is weakening of the notion of group, because the left inverse and right inverse are not the same. They have to be different, otherwise the whole thing doesn't work. So right? So what you do now, in order to verify that a sentence is well formed, you take your type. So for example, here you've got a noun, subject, then a transitive verb, which is this composite, then another noun which is the object, and then you just use your algebra to basically cancel out these two nouns with their inverses. You end up with a sentence, and this actually shows that noun, transitive verb, noun gives a well-formed whole. So this is this grammar algebra. this worked for pretty much all languages. Of course, the word order may be different in different languages, but a sort of algebraic structure sort of encompasses different languages. This is really old stuff. Well, old stuff in, yeah, pretty old stuff. Now, another way to represent the same is diagrammatically. So I just did a mathematical calculation. I said like, okay, you see the noun and the -1 noun, they cancel out. You see the noun -1 and the noun, they cancel out. And only the sentence stays, remains. So now I can represent this diagrammatically a little bit like annihilating, so that the noun and its antiparticle, so to say, -1 noun, they cancel each other out. Here, this noun -1 and this noun, they cancel each other out, and I can represent this by such a cup shape, and then the sentence is retained. So this calculation, verifying grammatical correctness, can be thought of in terms of this diagram, and that's going to be really important later. So from now on, we will think, so basically you now have to think of grammar as sort of structures involving these cup-shaped things and maybe straight lines and things like that. So that's basically a representation of grammar, showing the proof that a sentence is grammatically correct. Okay, so now we know a little bit of grammar algebra. So at the same time in Oxford, there was somebody else, Steve Clark, who's now back with us with me at CQC as our head of AI. And he knew vector space natural language processing. Now, what is vector space natural language processing? That's what everybody in machine learning is using now. You take meanings of words and you represent them in a vector space. And then you think of the distance between, or the inner product between these words as how relatively related they are. So two words which are very close to each other, maybe synonyms, will be synonyms possibly, and things which are far apart, very little relationship. So these, what I'm just talking about, are actually two aspects of language. One is like the structure of grammar, and the other one are the meanings of words. And these things are used in practice. Actually, the second one is much more prominent these days than the first one. In the previous century, the first one was a big object of study, because you know names like Chomsky. In this century, it's all the second thing, all this vector space. However, at the time around 2008, so I didn't know anything about language or something, but then Steve asked us the question, how can we combine grammar and meaning? There was no theory, that didn't exist at the time, a way to combine the grammar, this grammar algebra, and this vector space meaning, so that you could actually ultimately compose meanings of words to form, say, the meaning of a sentence. So the sentence is made up of words, I happen to know the meaning of the word, I know the grammatical structure, can I produce the meaning of a sentence? I mean, it's an obvious question, and you all know that there is no theory used out there at the moment, because if you play a bit around with Google or something like that, you quickly realize that Google doesn't understand grammar. Google search doesn't understand grammar at all of the sentence you type in. So that stuff didn't exist. So what was the solution to this problem? So we solved this problem. The solution to this problem was something I was working on at the time called categorical quantum mechanics. Categorical quantum.
Can I ask a quick?
Yes.
Can I ask a quick question?
Yes, sure.
Can you give an example of the first grammar algebra where you have the noun and the inverse? Just any simple example.
I mean, you mean the mathematical structure? So it's called.
No, just like an actual example from English. You know, like noun, inverse noun, that kind of thing.
Oh, this is an example. This is an example from English I gave. Right? This is noun, transitive verb, noun. Alice loves Bob.
Okay.
So so this is the most basic sentence. You got an object, you got a subject, you got a verb.
Right.
I mean, in another language, the order will be different. So in fact, for all possible permutations of object, subject, transitive verb, there is some language in the world where you use it. But so in that case, your composition of your transitive verb would be a bit different. So if for example, both the object and the subject would be in front of the verb, then the 2 n minus 1 would be in front of s. So in language, you have to construct your type somewhat differently.
No, I mean, so Alice and Bob, those are two n's, right?
Nouns, nouns, yes.
They're the right. And then what are the inverses? That's the part that I don't.
They're part of the algebraic structure. The way to think about these inverses is if you look at this -1 n s n minus 1, which is the type, composite type of a transitive verb, what it means, the way to think about this in inverses is this transitive verb wants a noun on the left and it wants a noun on the right in order to form a sentence. It's sort of, please give me a noun. The inverse means I want the noun. And
okay, so it's like a socket.
It's a socket. It's a socket in which you can plug something in.
I see. Okay, thanks a lot.
Or an input wire, an input wire. We'll see this later. This is really like an input wire, in which you can stick an input. That's what the -1s are. So they refer to the absence of a noun. They refer to the absence of a noun. And then by sticking a noun, they cancel out. Does it make sense?
Yes, yes. Thanks a lot. Thanks a lot.
Yeah. So what I'm saying is like, so you want to compose this algebra with these vectors meanings, and I said the solutions came straightforwardly from something I've been working on at the time called categorical quantum mechanics. Basically, categorical quantum mechanics was a new way of formulating quantum mechanics where the tensor product is the prime actor. Now this is quite prominent in quantum foundations. All people use this diagrammatic representation now. I saw Lucian is here. He has been doing this for a long time. Giulio Girabelli uses this all. So this is now quite prominent in quantum foundations, this using of diagram. At the time, it was just starting to build this thing. Now there is this book which you can have here, Tips in Quantum Processes. It's been translated in Japanese and Russian and Chinese. So it's doing reasonably well. And there you find a presentation of quantum theory entirely in terms of pictures. Now these pictures are not illustration, they're totally rigorous algebra. Mathematically they correspond to monoidal categories, but we avoided to use the language of categories when presenting it, so that people actually want to read it, because a lot of people sort of say, oh, category theory, don't want to have anything to do with it. So that's this categorical quantum mechanics, and magically, like I said, this solved the problem in a canonical way of how to combine meaning of grammar. Why? I mean, I can explain this very simple. So we're dealing with vector spaces. Actually, these are inner product spaces, because the inner product for these meanings, because inner product really is key in the application. So we've got inner product spaces to represent, say, systems, think of words as systems. So you've got these inner product spaces. And then you've got this grammar algebra. And if you know category theory, and you look at the particular structure of, say, these pre-groups, which I said is like this weakening of a group, it's exactly the same categorical structure as you find in quantum mechanics. If you consider entanglement and Bell states and things like teleportation, it's on the nose the same structure, the same category. So we got categorical quantum mechanics, which comes with this compositional structure, which perfectly matches grammar. And the spaces are vector spaces, so boom, you combine the two. And this is not just a theoretical thing. We kind of did experiments, practical, with real language and stuff like that, and we outperformed everything else which was around. So this was genuinely a solution. Let me now talk about categorical quantum mechanics. Categorical quantum mechanics is really a theory of wires and boxes. So you represent your systems by wires, like in a circuit, and then you've got processes which you represent as boxes. So you can have states and effects and things like that. And then you build diagrams. Now, the key thing is that your wires don't always have to go straight like in circuits. You can also bend wires up and bend wires down and stuff like that. And that actually gives you, that in its own, having these abilities to bend wires, they kind of already enforce the tensor product structure on you. They enforce, if you say my wires correspond to vector spaces, then automatically you get the tensor product as the way to combine system. You can't avoid it, it just comes on you. So in a way, this realizes sort of what I would say Schrödinger's dream, to have a quantum mechanical formalism where the tensor product is sort of the prime actor. Because really composing these boxes is really using the tensor product all the time. There are no sums. Now, you can think of these pictures as generalization of Dirac notation. I mean, I've got this little triangle here. Think of it as a state. You rotate it a bit, you chop some pieces off, you get a cat. You take this one, you chop some pieces off, you get a bra. And if you compose them, you get a bracket. So it's really a two-dimensional generalization of Dirac notation, these pictures. But they're very powerful. For example, I'm not going to explain this. What you see here is a full proof of quantum non-locality. This is the full proof Mermin style that quantum mechanics is non-local. On the left-hand side, we do calculation in quantum mechanics, we get something. On the right-hand side, we prove something about any local theory, and you get a contradiction. It's as simple as that. So it's a very powerful formalism, these diagrams. Okay, let's go back to language. So it was in this paper that we said, okay, we know how to put together meanings of words and grammar. And okay, this was the result, this paper. The three of us, I mean, the way it works, it's very simple. I mean, you remember this sort of shapes, these cup-shaped wires I came up with. So the way to think about this is simply, you have a meaning of Alice, you have a meaning of Hayes, you have a meaning of Bob, and then you apply to it as a process, the proof of grammatical correctness. Now, intuitively, what happens is basically that Bob, and so I said you have to think of these n-1s as inputs. You can really see the meaning of Bob going into Hayes, and the meaning of Alice flowing into H through this wire, and then H output the meaning of the sentence. So these are the meanings of words, this is the grammatical structure, and you put them together. You just compose them, just like you could. And people who know a bit of quantum information, they will recognize this as a quantum teleportation protocol, a fancy quantum teleportation protocol. You got Alice as your state that you want to teleport, but you also want to teleport Bob. You want to teleport both. And you think of Hayes as your resource state. And so you use your Bell effect here, you use your Bell effect, and then Alice and Bob together will be teleported through Hayes, which then also acts on, and this spits out the meaning. So you can interpret this diagram both as a physical protocol, like sophisticated teleportation, or as a computation of meaning of the language. So these two things are exactly the same, representing meaning, representing physics. And then you can do some more stuff. Yeah?
A question. I understand you have a vector space of meaning of words, but does this produce, is there a vector space of meanings of sentences also? Is that what,
well,
what is the output of your thing goes into?
Good question. Let me get back to you later. So at the time, we were hacking things together. So, I mean, you can think of an event space maybe. So think, I mean, for now, just think of it as an event space where everything that you can describe lives. But we're going to do better later. So just think of it as an event space. But indeed, it's a very good question. What is the sentence space? How does it relate to the nouns and all that? I'm going to solve this later. I'm going to solve. For a while, we were just hacking things together. Now, a thing you can do is now be smart and say there are some words which are sort of more logical. And so you can actually attribute a specific structure to them. So you would expect and or to be statistical vectors or something like that. You would expect them to have some more logical structure. And one of the words we quickly sort of gave logical structure were relative pronouns. So for example, here we got a sentence, she who hates Bob. She who hates Bob. And in quantum physics terms, the dot which you see with 3 wires is actually a G at Z state. That's the G at Z state. The other dot is a little bit like deleting. So in categorical quantum mechanics, we got this thing called spiders. So if you look at our book, then you'll see the spiders everywhere. And spiders are basically just things which you build given a basis. So examples of spiders are just a copy operation. A copy operation, you take one basis vector, you copy it. Or you take you take 2 basis vectors and you compare whether they are the same. And if they're the same, you output them. If they're not the same, you throw them away. So like a Dirac delta, they're kind of a big Dirac delta in a way. But they're really important. And so we use them in the language to do things like representing relative pronouns, stuff like that. And they have a very beautiful, behavior. You can check that these things, if you compose them, they again give one of them. And in fact, this single equation actually axiomatizes them. So they're easily axiomatizable by saying spiders fuse together. So that's why they make it so easy to do diagrammatic reasoning. They're very beautiful mathematical objects. And so we use them both in quantum and in language. Okay, so now some meanings of words are more logical. This will be important for what we do later. What you can do now is I've got, for example, the meaning of a sentence in whatever space it lives for now. One sentence, Alice does not like Bob. I got another sentence, Alice hates Bob. And we can now, for example, compute in the products to see, do they have related meanings? In this case, they would be very related in meaning. They say very similar things. And so that's the reason why you want to have meaning of sentences, because you want to start comparing meanings by your product. So that's kind of how this stuff works. I mean, at the time when we came up with it, we got a lot of media attention because it was like sort of a big open problem. But people were kind of saying quantum linguistics, and we were saying this has nothing to do with quantum. This is just like we just use quantum formalism to solve a problem in language. I mean, little did I know that little did I know, I'm going to skip something, that as we speak today, we're actually sticking all that stuff on quantum computers, and we do natural language processing on quantum computers. So we do this with like corpora of more than 100 sentences. We're doing this today on actual quantum computers, like teaching the quantum computer thing, asking. That's why I'm in the private sector now. That's what we do, these sort of things. So little did we know at the time. And since this is a quantum gravity seminar, I think it's nice to also make the following analogy. Like the first time in the beginning when we were talking about this, like 10 years ago, Lewis Crane, who I think many people here know, he said, hey, this is grammatical quantum field theory. Why grammatical quantum field theory? Because topological quantum field theory, TQFT, is you take these topological structures called cobordisms and you map them on vector spaces. That's what you do in TQFT. What we do here is we take very similarly looking structures, these cups and these caps and these spiders, and we map them on vector space. And in fact, categorically, they are the same type of category. These cobordisms or this grammar, they are all the same kind of category as this pre-group grammar. So it was actually a very good analogy. Essentially, and I'm saying this because Carlo is listening, these categories are really categories of relations. They really embody what relations are about, these sort of categories, but they are relieved from the constraint of concrete mathematical relations that they are about true and false. So concrete mathematical relations, they're about true and false, and it's very restrictive. It's very restrictive. So these are sort of generalizations which are not about Boolean, but completely have the spirit of relations. They have the soul of relations, I should say. So they're very and so quantum mechanics is completely built with them. Okay, let me now. Okay. So I don't have that much time, but I want to go to the spaces. So first, so Carlo asked about like vector spaces as meaning. Now vector spaces, what are vector spaces? They're basically spaces of statistics. They're statistical beasts without any structure. Von Neumann hated them for that reason. Model theory people, they've proven that you can pretty much stick everything in a vector space. And the reason it's used in NLP and machine learning is because it's statistics. It represents statistics. Now, if you think about meanings of things, then you might be able to come up with something better than a vector space. And a first example we worked with, and we did exactly the same as we did before, were something which was called conceptual spaces. There's a developmental psychologist called Peter Karlofors, who has a theory about conceptual spaces, and they're typically convex spaces. I give a few examples here. Okay, that's a very simple convex shape. These are tastes. This is a more sophisticated convex shape. These are colors. And they can get very complex, these conceptual spaces. But the sort of game I was playing before with grammar and meaning, you can do with these spaces too. Because the theory is sufficiently abstract that you can actually come up with any kind of space. The moment you can organize them in some relational category, you can play this game of composing meanings. So that's interesting, but the most interesting space of all, I would say, I mean, this is a side remark. You can think of this conceptual space theory as GPTs, which I know a lot of people here are interested in, GPTs with composition. Anyway, that's a side remark. The most interesting space is space-time. Why? I mean, it's all around us. So if you look at language, let me skip here. Lots of stuff in language, like propositions, in, next to, after, on, they're all very spatial. So many words and phrases and sentence and text meanings, they're all related to space, one way or another. There's so much space in meanings of words. When we act in space and talk to each other, we use pointing and other kind of references. And space is also where we live and embody. It's like one of the things AI learned a long time ago is if you don't give a robot a body, it can't do anything. It needs to sort of have this interface with the space where it is. It's an important lesson from robotics. And one may even think that physical space was a theater where actually language emerged when we were hunting mammoths and stuff like that. So it's a really key thing. So why not just take physical space as at least part of the space of our meanings? So that's what I'm now going to try to do. So it's in this very recent paper with Vincent Wang that we built this thing. We've been trying to do this for 5 years, I understand. We always failed. Okay, so what is a space? Here are a few examples of spaces. The first one is just a really lousy picture of a Euclidean space. The second one is like a subway line. The third one is Penrose staircase. The fourth one is a chessboard. So they're all physical spaces in which can be inhabited by agents and stuff like that. They're all physical spaces. I mean, a physicist would typically think of the first one. We didn't do relativistic. I've got a student actually looking at relativistic paradoxes within this theory I'm now going to tell. So you can do cool stuff beyond like these naive spaces. Okay, so what is the sort of thing we want to do? We want to capture space in meaning. And for example, if you see this sentence there, the pawn next to a king that a knight can capture. If you look at a chessboard, there is one particular piece which obeys that description, which is the one in green. So that's a pawn next to a king, it's next to a king, and a knight can capture it. I mean, you can look around, there's no other pawn which obeys the description. So the challenge now is to come up with a theory of spatial meaning such that if we compute that diagram, we get that pawn exactly. So we want the theory of space that respects linguistic structure and the way we sort of put linguistics meanings together. It's a very natural thing to do because space is so important. It's a much more natural meaning space than vector spaces, I would say. It's a sort of simplest basis case. So how do we do that? How do we do? Okay, so something else we want to do, I forgot to say, is if we've got a sentence, the painting is above the chest. The light is above the painting. We want to be able to infer that the light is above the chest. It should be part of your theory of meaning too, that you can actually make inferences, or Alice chases Bob, Alice is in Paris, Bob is in Paris. You want to make these sort of inferences too in your theory. And there's many more like this. These are two very naive, simple examples. Okay, how are we going to build our theory? It's going to be a theory of relations. So a lot I'm saying is all about relations. So we take a very naive, you can probably get a much more structured theory of space, but this was good enough for what we wanted to do. We just take a monoidal subcategory of relations. So relations, what does it mean? The category of relations has sets of its object, but in this case, we just take spaces or multiples of spaces. So one thing we discovered when trying to build this is that if you got more than one agent, then each agent wants its own space. Each agent wants its own copy of the space. Otherwise, it just doesn't work. We tried for a while to get multiple agents within one space, but no, each agent has its own copy of the space. Of course, they're all the same spaces, so you identify them, but it's really necessary to make this work. Then you got relations. We call them spatial relations, and I'll give a whole bunch of examples of them, and they express how things relate within space to each other. And then finally, you need to be able to compose these relations. So you want to compose them sequentially. So this is just so just like you compose two functions, you can compose relations as well. It's a very simple definition. You compose one relation with another. You can think in terms of Venn diagrams. You have one Venn diagram for one relation, you have arrows, then another one, and if there's an arrow from the beginning to the end, through the middle, then that set of elements is in the composite of the relation. It's a very baby set theory stuff. I mean, in my generation, we learned this when we were 6 at school, when they were teaching set theory when we were 6. So this is sort of the Cartesian product of two relations. This is just putting two relations in parallel. So this gives you the monoidal category of relations, but we restrict to just physical spaces, multiples of physical spaces and objects. So how can I translate words in this relation? For example, here are two examples. Move right. Move right is the relation which relates a place on the chessboard to the place to the right. Or king's moves is a relation. King's moves is wherever a king can move to, from where it is. So you can express this as a relation. So this is for the chessboard, for the subway. So next stop is a relation. In between would be a relation. This is a relation between three things. One thing is in between two other stations, for example. And you can also have a relation just be a single in a single set. So, for example, my station. That's a trivial relation. It's called, that's a state in the world of relations. It's a subset. Typically, it's a subset. Okay. Here, this is an Euclidean space. Higher than, I can write down higher than. I can write above, which is a little bit different. I can write down chases. I mean, the explicit descriptions here is not important, but it's very trivial. It's very trivial once you get the gist of it to come up with these relational representations of words. Okay, and then the important thing, we have these grammatical structures. So these things, in quantum mechanics, there would be things like Bell states. There are also corresponding relations. This is just the subset. This is the subset where you take one set, you take Cartesian product with each other, and you take all the identical pairs. You just take all the identical pairs.
Bob, just to get a feeling of what you're saying, when you say it's like Bell states, so what is the entanglement in the words?
Oh, so this is the relation that expresses perfect correlation. I've got two sets, X and X, and this is the relation that says if you take X0 on the left, you have to take X0 on the right. If you take X1 on the left, you have to take X1 on the right. You can actually write this thing, you can write all this theory of relation down using Dirac notation. Just use your usual Dirac notation like in quantum mechanics, but only use zeros and ones, nothing else. So you write down your matrices, you write down your Bell states, you do everything the same as you would do in quantum mechanics, but only use zeros and ones. That's what I'm talking about. That's exactly what I'm talking about. Then this product corresponds to the tensor product.
But is there a sense in which these correlations are not classical?
That's so you can use this category of relations to prove non-locality. So the abstract non-locality argument I showed, it works here. In that sense, there is something quantum here. Now you don't have phases, you don't have phase information, so you're not going to get inference and stuff like that. So Rob-Speckens' story theory, is a sub-theory of this. It's a sub-theory of this. There's a paper, I think it's called toy quantum categories, where we show that Rob-Speckens' toy theory is a sub-theory of this, for example.
Okay, thanks.
Okay, next on. Okay, so now I'm going to try to prove this, that this chess piece there exactly corresponds to the sentence, the pawn next to a king, that a knight can capture. So the first thing you do is break this sentence down in pieces. So let's look at the pawn next to the king. Okay, you see I take a particular form for next to. I don't have time to explain why we take this particular form, but it's just that certain words have natural smaller representations using these dots. I'm not going to get into the details here, but just accept this is the pawn next to the king. So we can deform this. This is just topological deformation. I'm doing nothing else. So what I get is I get the pawn and I get next to a king, and this dot in the category of relations is like intersection. It's really taking the intersection. So this would be a subset. This would be a subset, and you take the intersection. Now next to a king, you can basically write like this. So this what I'm doing is I've got this wire here and I'm just pulling it up. This is like transposition. This is like transposition of matrices. Partial transposition works exactly the same in relations as it works with linear maps, because you're just working with matrices with zeros and ones. So now we see we've got this would be a subset, the king, and then you apply the operation next to it, and this gives you then the outcome of next to a king. So basically what we got here is we got the intersection of the pawn next to a king. So we can now see on our chessboard, this defines a pawn, this is next to a king, and this operation dot actually, where is it? Yeah, dot gives you intersection. So you end up with this. All these green things here on the right are valid So you get a subset, because you get a subset consisting of these three bounds. That's what you get as the result. This is calculation. As a result of the calculation, the pawn next to the king. That's what you get. So we're not there yet. Now we want to say that a king can capture. This is much more interesting. This is a much more interesting part. Okay, let's first simplify it. So we can just do some fusing of dots and stuff like that. And you end up with this. A knight can capture. This is really interesting. Can capture depends on which chess piece is actually capturing. Can capture is not a universal thing. It depends on its input. So we are missing something in our theory. What we are missing in our theory of space is that inhabitants may be different spatial capabilities. Each chess piece, think about a horse or a knight. For the topology of space for a knight is very weird, because the thing next to it is not close. It can only make certain moves. So it's actually stuff which is further away, which is closer than the thing next to it. So we need to, one way or another, we need to get these particular features of these agents in space also as part of our theory. And the way we do this is by extending our theory of space from, say, the chessboard to also specify what are the possible inhabitants of my space and their spatial capabilities. Like how is, so it's the space from the perspective of the inhabitant. It's like, think of it as a relativistic perspective. It's very similar to a relativistic perspective. So it's the space from a perspective of the inhabitant. And the way we can encode this easily, we say can capture, we give can capture this shape. And basically what it does is it takes in the position here, but it also takes in of the specific agent its spatial capabilities, which we express as a spatial relation representing the possible moves. So if I now yank this, what I get is actually the position comes in, then the moves act on it, and we get exactly what we want from can capture. So this may be the most interesting part of this entire theory, sort of accounting for. This is not the only way you can do this. So what we did here is we actually attribute the capabilities to the agent. We could as well have attributed the capabilities to the word can capture itself, but that sounds really stupid, that the word can capture sort of encompasses all the information of anything that ever can be changed in something else. So it's much more natural to have the agent itself say, hey, this is what I can do, rather than some universal collection of everything that any agent can do within the word can capture. So this is a nice way to make can capture a very simple thing. And now we've got the pawn next to the king, then a king can capture. You see there is this dot in the middle. So essentially we're just doing an intersection of what we found before, the pawn next to a king, and then the knight can capture, and we end up with a. So this is now a full relational calculation, which gives us the exact meaning that the sentence intended to be. Here is another example, like the ostrich next to a tree that a cheetah next to grass can capture. Here the sort of spatial abilities will be the speed of the cheetah, its endurance, speed of the ostrich, its endurance, and they will then actually define the can capture sort of ability. So, right. I'm running out of time. Maybe I should stop here. But this is actually now I'm going to answer Carlos' question about the meaning of space, sentence space. Should I do that?
Yes, it's okay, but we interrupted you several times.
Okay, so now I'm going to answer. So there is a new. So all we have been talking about, and all which we are doing till recently, was about putting words together in a sentence. So what about putting sentences together in a text? What about that? If you remember all our sentences, the meanings was just a vector. So now a vector is like if you think about composing sentences, think of sentences like gates in a circuit. They have an input and an output, so I can put a sentence after a sentence or a sentence before a sentence. But if you got a vector, you can't really compose them properly. How are you going to put vectors together? So there's something wrong with this entire theory of representing sentences as a vector. And in that paper, which is fairly recent, I think 2019, I see. So I extended this theory from composing sentences, composing words to sentences, to composing sentences to text. And in the process of doing so, we were forced to pick out a particular representation for the space of sentences, which feels that we never thought about it before. And this kind of forces to make a pick which is very natural. Let me do that here. Okay, come on. So this is what we're going to do. And so here you see the verb hates. So you got the noun wire on the left, a noun wire on the right, and then this mysterious sentence wire on the left, in the middle. So what I'm going to do now is I'm going to use my dots, which I've been using a lot, and I'm going to represent hates as a much smaller vector, a vector just with two nouns outputs, and then I copy one to the noun position, I copy another one to the noun position, and I take the two other copies to be the meaning of the sentence. This may seem mysterious now, but I'm now going to explain why this makes perfect sense. So if you do this, this is kind of a substitution. I make a substitution inside hates of a different form of hate, which is composed of three things. If you do this, so now we got Alice hates Bob, I can do the following. I can basically deform this diagram as follows. So I now make this Alice wire straight, I make this Bob wire straight, and then I can think of hates now, I can think of hates as entangling Alice with Bob. So I got an Alice wire, I got a Bob wire, I think of the wires as my nouns. What the verb hates does, it entangles Alice and Bob in a certain way by means of a hates relationship. I mean, this could also be love, this could be marries, this could be whatever. But so they get entangled. So this is exactly, the reason I can do that is because of this form I chose. This particular form where my sentence, the meaning of the sentence space corresponds to the spaces of the nouns in the sentence. And what I can do now is I can start composing sentences. So I've got three agents, Alice, Bob, and beer. Alice hates Bob and Bob likes beer. And I can go. Alice maybe destroys the beer after because she hates Bob. And so you can go on forever with whatever complexity of sentences. So
Bob, can I ask?
Yeah.
So the thing is that when you say Alice hates Bob, right, it doesn't necessarily imply that Bob hates Alice.
No, it's not at all symmetric.
So the thing is that in the language, there is a certain directionality, right? But if you talk in terms of entangling two different systems, then there is no directionality in that.
No. These quantum states are directional. Entangled states can be directional. They're not symmetric in general.
No, I understand that, but like here, there is no concept of directionality in this diagram.
Oh, there is. The direction is built in. The direction is built in the representation of hates. So the hates you can think of as a matrix, and this won't be like a matrix which is equal to its inverse. You have to think of like hates and likes as matrices. They're bipartite states, but a state on two systems can always be represented as a matrix. So these are matrices, and they don't have to be reversible even. They don't have to be reversible even. They can be anything. So there is a clear directionality. I mean, if you think of it as it looks like a symmetric box, but it's not at all. Just like any box, any quantum gates is not equal to its inverse typically. So they're totally non-symmetric in general. I mean, there are symmetric ones like marries. Marries would be symmetric.
Right.
But in general, they're not.
Right. Okay.
I suggest we leave Bob to wrap up, so we give a chance for other people to ask questions.
So the reason I was showing this was then to now, because I said we want to make inferences, now we can actually use this composition of sentences to make inferences. Like I'm not going to go in details, but light is above the painting is above chest. You can actually deduce from that effectively. Oh, come on, move. Now come on, why aren't you moving? Oh. Why aren't you moving? Okay, I'll just scroll. You can actually derive from this that the light is above the chest by basically deleting the agent in the middle. That's about it. I'm just going to leave the slide. So now what you can start doing is, for example, combine your space representation, maybe with tastes, maybe with color, and you can now start speaking about meanings like the cheese inside the suitcase stinks. So we can now actually so this is much more interesting as meaning spaces than vector spaces. We can build a meaning space, for example, based on our human senses. And we can represent meanings and relative to our human senses. And for example, from a perspective of AI or robotics, this would make a lot more sense because in a way, you're giving the robot a body, just the same body as we have, by using these meaning spaces. Okay, so I'm going to end here. So maybe I've got some more slides, maybe they come up in the questions. Thank you.
Thank you very much, Bob. All right, let's see. Let's start by Andrea Di Biagio. Andrea, were you clapping or you had a question?
I was just clapping, actually.
Ah, okay.
Yeah.
Thank you.
Gislan has a question.
Yes, thank you. It was a great talk. I enjoyed it a lot, and now the next thing I want to do is just dive into all of this because it seems particularly elegant. I had two questions, but I will only ask one for now. This is incredibly close to Roger Penrose's diagrams, for example, that look like this. And I was wondering, because these are tensors, and you spoke of matrices. Is it the same thing? Is it a subset? Is there a mapping in any way?
Well, it's so the general notion of Penrose diagram, not the sort of specific ones you just showed, but just the idea of like putting boxes together in mind is exactly the same thing. It's exactly the same thing. What we did initially was specialize that to the particular case of quantum mechanics. And we did this the spiders I showed is something you need there. This is like a key thing. Basically, we got spiders of two colors corresponding to complementary observables. And then you can actually produce a theory which is such that anything you can prove in Hilbert space using matrices, you can prove just using diagrams. So but the starting point is the same as the Penrose diagrams. It's just that we fill it in with very specific graphical ingredients, in our case, the spiders of two colors, which for those people who know quantum group, they interact like a Hopf algebra. They then interact like a Hopf algebra. If you say then there's just one equation which you need, which is kind of specific to qubits to come up with this theory that whatever you can prove with matrices, you can prove with these diagrams. So, but it has the same origin. These are Penrose diagrams. These are specializations of Penrose diagrams.
That's great. Thank you.
If you look in this book, it's full with that sort of stuff. It's full with that sort of stuff. Right.
Thank you. Let's go to, thank you, Gislam. Let's go to Lucien.
Hi, Bob. This is a great talk. Can you prove something or investigate something like sort of universality in the sense that you can construct sentences that reach any point in your sort of meaning space? And sort of following on from that, can you imagine if the answer to that were no, or even if it was yes, can you imagine sort of inventing words that don't currently exist in the language that would help you get to those places that are impossible or difficult to reach?
That's very interesting. I mean, I was just talking about like the completeness result we have in the case of quantum mechanics. So there we know that our spiders of two colors are universal. You can reach any matrix, and moreover, you can prove any equation just using diagrammatic stuff. Now, here it's a little bit more difficult to. So there we've got a reference, which is the Hilbert space. The Hilbert space is accepted as a representation of all quantum states, all quantum meanings. Mm-hmm. Here it's more tricky. What is the space of all meanings? I mean, is all the words of a dictionary? There's probably more, because sometimes what we do is we take a sentence, we compose stuff, and then after a while, that sentence gets its own word as a description. Like, you kind of see what I'm saying, like, because it's something you were using, and also we start giving it a name. Yeah. Literally with the sentence, the child of Alice and Bob. Okay, well, let's call her Mary. Now she has a name much shorter than the child of Alice and Bob. But what you say is incredibly interesting. So we have been developing this theory of circuits for language, because actually that's a new theory of language, which are sort of indicated by turning this language into these circuits with gates. That's really a complete new theory of language, which then allows you to compose sentences into text. But it does more. It sort of tells you what sort of gates you can have. So you look at English, you look at all the words in English, and English tells you you can have at most ternary gates, like a gate with 3 input wires and a gate with 3 output wires, and that corresponds to a ditransitive verb. The way you think about this is ditransitive verb represents an interaction of 3 systems. It's a 3-system interaction, but there are also 4-system interactions, but it turns out we have no words for that. That's one example of something that could be useful, but we don't have. A 4-people interaction, like a quartet, you could, a quartet is a canonical thing of 4 things, but there is no verbs to connect 4 things. We just don't have them. Maybe in some, I mean, definitely not in English. And yeah, I mean, obviously, like when you build a meaning space, just the vector representation, you can just pick any vector in there. It's supposed to be a meaning of something, but then typically there's no word, because obviously all the words we have never going to be dense in a vector space. They're never going to be. They're never going to be. So we've got words probably, we've got words for certain, going now to the more interesting one. This more interesting combination where we've got different spaces. We got words for which sort of certain entangled states across these spaces. For example, banana is an entangled state across color, taste, and texture. You can have a green banana, which is bitter and hard. You can have yellow banana, which is sweet and soft. You can have a black banana, which is like liquid and mushy or whatever. So that's an entangled state across 3 spaces. So you get these concepts too, and certain entangled states are going to be impossible. You can't have like a green mushy banana. So that's again stuff which lives in the space, but which is kind of impossible. So there's a lot of interesting things to think about there.
Okay, well, thanks. That's interesting.
Thank you. Thank you, Lucien. So let's go to Pierre.
Hey, thank you for the talk. I have a question.
It's very, very quiet. I can't hear you.
Okay, let me.
Is it better now?
I have a question of linguistics. So in semantics, a big question.
It's down again. I don't hear you again.
A question.
I don't know why.
It's okay now, Pierre, but speak louder.
Okay, so it's a question of linguistics. In semantics, there is a question which has been discussed many times, which is how does the meaning of a sentence emerges from the meaning of the words? And my question is, considering your recent works, when we are trying to go from the meaning of sentences to the meaning of the text, is there something which is essentially different that happens, or is it basically the same thing?
Okay, this is a really good question. So what you're talking about is what typically is referred to as compositionality à la Frege. So compositionality à la Frege means that the meaning of a whole is determined by the meaning of the parts and the structure. So in this case, the structure is the grammar. And I mean, I kind of start to tell my whole story like that. So when you go, so I kind of already, now your first question was how is going from sentence to text different? I kind of already explained that what we need to do is to think of nouns as very different beasts than all other words. So we think of nouns as agents, and they form the wires in a circuit. They're like special roles, they're agents. We think of nouns as some nouns don't need to be taken to be an agent. By default, you can take all nouns to be agents. And then verbs are actually gates which act on these agents. And this completely changes the interpretation of what we think about nouns. Because now we think of a sentence as something that modifies the meaning of a noun. In typical in the first part of the story, I thought of Alice and Bob as static vectors. There is an Alice vector, there's a Bob vector, and they're always the same. This doesn't really make sense that Alice and Bob vectors are always the same, because a lot of stuff is going to happen to Alice and Bob, so they become different. And in the new representation with the circuits, it is like that. You got Alice and Bob initial state. Then you start to applying a gate. Maybe they're married. Then Alice and Bob are not even separable states anymore. They're not even separable anymore. They're entangled. The state which comes out of separable Alice and Bob after married is entangled, of course. So it's a completely different conception of nouns that you need to do to go from what. So basically, again, related to Carlos' questions about sentence spaces, in traditional grammatical calculi, like Chomsky and all that, sentence space was a fixed thing, was a fixed type. There's only one sentence space. Now here, this is not true anymore. If I've got a sentence with an intransitive verb, like Bob drinks, then the sentence space is a noun, a single noun. If I got a transitive verb, Alice hates Bob, then the sentence space is two nouns. If I've got a ditransitive verb, for example, Alice gives flowers to Bob, so I got three nouns, then the sentence space will consist of three nouns. It will be a product of three nouns. So that's a completely radical change. But it sort of makes sense, because what is the space of all sentences? It's almost an absurd thing to think of. It's almost an absurd thing to think of. While thinking of a sentence as something that alters meaning has a lot of advantages. It means your meanings are not static anymore; they evolve, which is everybody knows GPT-3. So GPT-3 doesn't know there was a COVID pandemic because it was trained before. So meanings don't, in typical AI, meanings don't evolve. They're all static. So this theory actually allows you to make meanings evolve. Now, here is a very important part. You said something like we can get meaning of sentences from words, we can get meaning of text from sentences. That's not really true. It's not a box of frame compositionality that from the bottom, from the small, you compute the big, fails drastically if you actually start to do practical stuff with language. So much meaning comes from above. So much meaning of words actually comes from the meaning of the sentence, or from the meaning of the wider text, or the location you are currently sitting, the space around you. And when people start to do machine learning, they very quickly realize that this is really important. The context is so important to define the meanings of the part. I mean, the naive case is ambiguous words like queen. Queen can be a beat, can be a chess piece, can be a rock band, can be a royal, can be a lot of stuff. And then if I say Queen plays tonight at Royal Albert Hall, then Royal Albert Hall tells me which queen it is. I mean, this is stuff we actually did experiments with how context determines meaning. But it's much more than that. If meanings of words get so much from the meanings of things we say, get so much from the broader context, that practically going only bottom up just doesn't work. That's practical. There's empirical evidence that it doesn't work. And I think this is really cool. Because and quantum mechanics is very suited to deal with that. Because if you think about an entangled state, the meaning of the whole is not determined by the meaning of the parts and the structure. Because if you take a belt state, there is no meaning of the parts. It's just noise. So everything you need to then reconstruct your belt state is the belt state itself. So clearly we don't have this sort of frame compositionality there. So, which is a good thing, I think. It's a good thing. It makes the world richer. And I think in physics, we need to think more like a lot of using this sort of formalisms for physics is kind of the same. It's also letting the whole decide the parts rather than just the other way around. So I think a lot of physics suffered a lot from too much bottom up, too much particle physics, so to say, too much particle thinking.
Yeah, thank you. It's very clear. But just to complete my question, I want to know if there is a difference in the kind of relation from between the words and the sentence on the one hand, and the sentence and the text on the other hand. I understand clearly that it's not from bottom to top, but in the relations between these two things, is it?
It's not really. I mean, it's not really that much, because if you take a sentence with a relative pronoun, let's take a sentence with relative pronoun. Alice loves Bob's book that he gave to Charles, something like that. So I can break this down in two sentences. Alice loves Bob's book, and Bob gave his book to Charles. So suddenly one sentence becomes two sentences. So in the first case, we're just talking about composing words to a sentence. In the second case, we're talking about composing sentences to text. But the end result is the same. Now, the thing is, of course, like the way I was presenting sentences, we don't do this anymore. These are old stuff, the word to sentences. For reason I explained, even there, it's much better to give circuit representation. Because it's just better, these circuit representations, for all the reason I gave. Meanings change, we have a good notion of sentence space, and all that. So it's one whole. In the circuit world, it's all the same.
Thank you.
Composing word to sentences, it's all the same.
Thank you very much. So now it's, thank you, Pierre. Now it's Roland Guichard, if I pronounce this well. And after that, it's Carlo Rovelli.
Hi, Bob. Yeah, thanks for the nice talk. I have a quick question about grammatical ambiguity, actually. Thing is, in other kind of systems or grammatical system like context-free grammars, you can really define ambiguity. I mean, ambiguity is kind of clearly defined. And here, most of the examples that you showed have unambiguous meaning, I guess, right? So yeah. How is it actually, how do you deal with ambiguity in there?
Okay, so there's a very good question. So first, you've got different kind of ambiguity. You got grammatical ambiguity and you got meaning ambiguity. So I gave the example of Queen. Another example is black metal fan. For example, a black metal fan can be, well, a black fan made from metal, or it can be a fan of the music genre black metal, right? And these two sentences actually have different grammar. They're grammatically different. So the way the adjective composes is completely different. So they would have a different diagram. So this is another kind of ambiguity where you don't really know how to assign grammatical structure. And modern parsers, they basically are probabilistic things. They kind of spit out the grammar, which is, so parser is a thing which figures out the grammatical structure of sentences automatically. So these things exist. So they typically spit out probabilistically what they think is the most likely parse. So with black metal fan, there is no most likely parse. So but they'll pick something. Now, how do you deal with ambiguity? So you all know quantum mechanics. There is this guy called von Neumann, and he was wondering, how do I deal with ambiguity in quantum mechanics? Like, if you got two vectors, and I'm not sure in which my system is. Okay, he came up with the concept of a density matrix. So you can do exactly the same here. If you got, I can take the meanings of Queen and build a density matrix. For the grammatical ambiguity, I build a CP map made up of the different grammatical parsings. So I'm basically just doing exactly what we do in quantum mechanics to deal with ambiguity. And we've done experiments with that. And then you see if you do something like Queen is playing at the Royal Albert Town, in the beginning you've got mixed states, but the overall meaning will be a pure state. Because the presence of Royal Albert Hall disambiguates, demixes, whatever mixings there is in the sentence. This works perfectly. So quantum mechanics gives us the solution. So I'm surprised that nobody else ever used density matrices outside of quantum mechanics, because it's such an obvious thing to do. It was invented for ambiguity.
Okay, thanks. Yeah.
Mario.
Me to moderate because
yeah.
The next question is by Carlo, and then it will be Tian.
Okay, we changed. Okay, Bob, great stuff. I loved it. Thank you very much. It was wonderful. I have a very specific question. Your framework give a lot of weight to nouns. They're sort of central in your construction. So the question is, and I guess it's an old question in linguistics. How do you analyze a sentence like "it's raining"?
So yeah, those are good examples. It's raining. I mean, this is a typical example that says how much context, how important the context is to start with. So this is like pronoun resolution. Typically, there are standard techniques to deal with pronoun resolution, but it's raining is a very special case. What would I say?
Well, let me put it this way. There is a way of thinking about language. It is about nouns and things that go around nouns, relations between nouns.
Yeah.
But there is another way of thinking about language that it's all like it's raining. It's about events, not about things. And isn't this compatible with your way of thinking?
I mean, in this case, you probably. So a lot of stuff in language, I mean, that's something we actually, I think is actually online, Razin. So some people, some of my students, they were thinking about negation. So when you say, for example, not wine, you don't mean a pink elephant. When you say not wine, it will be beer, maybe water, whatever. So there is some sort of worldly context always present, in which place your language takes place. So you may be sitting in a restaurant and then you say, not wine, then this is about drink. So I think there is something needed explicitly in this framework, which is the context, the place, the location where you are, and the it's raining would then be an attribute specifically to that. But I haven't thought, I really haven't thought, I mean, this is very recent work, I must say, like, so I haven't put too much thought into this sort of worldly context. There are a few papers out now by Razin and his colleagues thinking about logical connectives and the need for such a broader context, but there's still a lot more work to be done like that. So what I can say, things where we use such a framework for here is we are trying to, and we use machine learning, we're trying to sort of make a machine become aware of the space around it, maybe learn spatial relations themselves from data and things like that, and how they interact and all that. So we're kind of giving it the context by hand. We're giving it the context by hand. But in the general theory, yeah, I mean, my view on quantum mechanics is a theory of context. It's all, there is this context out there, and that's basically how the theory is set up. But we haven't nailed it down yet properly, otherwise we would have solved the measurement problem or something like that. But I think it's the same here. It's very much the same, that there is this broader context always present, and it's much harder here to grasp what it is. And that has to do with sort of embodiment in AI. You have to give a robot a body for it to do anything. It has to be living in a certain space, being in a certain place to be able to do anything. And with it's raining, it's the same thing. I mean, it's raining, yeah. It means I'm here in front of my window giving a talk, and it's raining means that whenever I look through the window, there's rain there. Or whenever I want to walk home, I'll be wet. So it's part of, it relates to this broader context of my general being and action. But it's not easy to characterize that. It's not easy. Good question.
So the next
question is by Tian-Sang.
Hi, Bob. Thanks for the interesting talk. I'm just wondering that your title is mentioned, it's about space-time linguistics. And I wonder how it's really related to time, because I see your about chessboard. So I'm thinking about that it may be like you, as I can imagine that an example in linguistics in time may be a story. And
So I had one example where time comes in. I mean, it's just a little. I just want to keep things as simple as possible. But here I had this one example I sort of flew over with about time, like here, the ostrich next to the cheetah, that the cheetah next to the grass can capture. So basically, there is a process in time taking place, and just like I was assigning to chess pieces the moves they can make, here this will involve the the speed a cheetah can reach, the endurance, and the same for the ostrich. So this is a temporal process. This is a temporal process. It just and there are many like Alice chases Bob. That would be another example. So in the paper we've got a few more examples about time, but it's a tricky one because we don't completely agree how to treat time, because sometimes you can actually have entanglements between time and space in this linguistic context. Like if you say you cross the river, then this can go in two directions. So there is some ambiguity, yeah, I mean, this stuff needs a lot more work, and time is kind of a tricky one. I mean, the next thing is to really think of space relativistically, because I think it's going to make sense. It's going to make sense here. It's going to actually make more sense than doing non-relativistic, especially when you're starting to talk about context and all that. But yeah, so in this example, there is time, but we just treat it pretty much as a 4-dimension for now, which is probably not the right thing to do.
And another quick question is also related to time, is because I noticed that you formulate because this is the story the linguistic in time may related to time, and then in time may related to causality, and you formulate causality in category theory in terms of this determinality. And I'm wondering that whether you have some determinality in this linguistic context.
I'm thinking you're talking about this paper. You're talking about this paper. So right. Yeah, so I mean, when you start making these diagrams like here, this is like from a scene from Once Upon a Time in the West. So you can make these stories. It's not just about language anymore. You can think of these diagrams also, for example, as a movie. I mean, I'm doing it here. Like I've put together like different movie scenes. You can compose them into a diagram, and ultimately, you can think of this as a causal diagram. You can totally think of this as causal diagram of events taking place, how they are related to each other. And now, I mean, now the nouns you can think of like world lines of agents within your physical space or something, or particles or whatever you want. And so you exactly get like a causal structure here. It's exactly the same as the causal structures in the work I've been doing on causality. It's exactly the same thing. And I really think of these diagrams which you get from language as some sort of logic of reality. Like it's not a logical system anybody has ever considered. For me, this is purely a logical system. So if you think about like a predator chasing prey, then I think of it as like you got two systems, predator and prey, and then you got an action taking place between, which is the chase. And and these diagrams are a generalization of that sort of logical structure. And I really think of this as logic of reality. And I think language, I mean, Chomsky thought that language was something very special that was to some extent even hardwired in our brain. I think of language, especially once you go to this form, which you can then generalize long beyond language and just general conceptual perception as a representation of the world out there, as the mechanisms in the world. That's how I think about it. So you can perfectly think of this as a causal structure like we think of causality in physics. Same thing for me, exactly the same thing.
Thank you, that's very interesting.
Thank you, Tian. Okay, we can go back to Gislam, since there's no other questions.
Yes, so I reserved my second questions for the end in case there were time. So,
no worries.
So there exist database technologies, storage and querying technologies that specifically store this kind of data. For example, Alice loves Bob, the cheetah next to the grass. For example, RDF, which means Resource Description Framework. And there's a whole ecosystem with concrete implementations and databases. There's even a language called Sparkle. And I was wondering if this is something you looked into, that potentially you could extend such a product with this contribution, because it sounds like it would be extremely powerful to have that embedded in a graph database, RDF based.
Yeah, of course, we have used these things in experiments because the data are out there, and so you get all these triples and stuff, and it's really useful. But typically they stop at 3. So they typically of the firm like object, subject, verb, and they don't go any further. So effectively, this sort of theory, and the fact that I'm private sector, so I can hire people to do a lot of work, generally enables to do stuff like you're explaining. And we're going to need this. We're going to need this. We're going to need this. We're probably going to build this automatically thanks to this sort of structures. It's this sort of structure exactly which will allow you to, because you don't want to do this by hand. You want to do this automatically, and it's exactly this sort of structures which allow to build like a data like that. Exactly. Like, I mean, we all, like I said, we also use these sort of structures to try to understand learning like a child, because machine learning is a black box. If you use these sort of more conceptual structures I was referring to, like this, they're much closer to our senses, and then you can start to understand how we can learn concepts, what sort of concepts are more easier learned than other, what sort of relationships between concepts are more easily learned. A thing you have to do that, so I'm going to show another paper here, is all this discrete stuff which I use today, like from the category of relations, is useless. You can't learn stuff when it's Boolean valued. You have to make everything fuzzy. So we have a fuzzy variation of the theory I was explaining, because it's the only thing that allows you to learn anything. That's learning. Make everything fuzzy.
So that's very interesting. So yes, there's a fuzziness and the fact that you need to support more nodes. Yeah. Thank you.
Thank you. Let's go to Lucien and then to Pablo.
Hi. So I think this is partly your answer to Tian's question. So you sort of evoked how language really is capturing something about reality itself, and so it sort of raises this question of whether you could think about this as a way to do physics. So in particular, could you, for example, actually make your work on linguistics interact with your work on quantum theory? Could these two things actually interact? After all, if you perform an experiment in a laboratory, you need to describe this experiment using words and the outcomes and so on. So it's very much linguistics is very much involved. So yeah, so that's the question.
I mean, yes, like when you go to these sort of diagrams, I mean, here in the case this is a film scenario, but this could just be a quantum diagram, a quantum protocol, a description of stuff you effectively do in the lab. This could be a picture which you see in a lot of the papers on like causal structures, quantum causal structure stuff. I mean, there is an interesting thing in the other direction. So we hired Robin Lawrence, you probably know Robin, to understand causality in language. That's a monster. That's super complicated. And the only useful thing around that helps us somewhat is all the work which people like John Barrett and Robin have been doing specifically on quantum causal structures. I mean, I know this project, a lot of stuff on quantum causal structure happened in there, and also the previous Templeton, which we had with Specken and co. But that stuff is the only thing around that's useful for us to try to understand causality in language, which is much more complicated than physics. From this perspective, physics is very easy, to be honest. This stuff is much more complicated. Although, again, like agency plays an important role. I mean, you know my work, so you obviously see that everything I'm using is the same stuff I used when we did categorical quantum mechanics. We use exactly the same pieces of language. Now the circuits are here, which we are talking about in causality. So there's incredible parallel. I mean, it's almost shocking. So
the question is whether it's more than just a parallel, whether you can get the two things interacting within the same theoretical frameworks. So not just analogy, but actual.
I think it's part of, I mean, so I had this title here, physics and everything, and that was basically starting to think about exactly what you say, because I've been thinking about that a long time. The question is, what is, I mean, something you start thinking about is, what is the role of physics in the world? Is physics something fundamental that underpins everything? Was physics just one phase of a much more global representation of the world, where also this sort of logic I'm talking about is an essential part of it? Like for me, I'm starting more to think that this sort of logic should play a role in physics. a new form of physics. So maybe, I mean, so I'm very glad that we're staying into the hopeful renewal of QISS, because I think that's exactly the sort of question I want to ask there. That's why I'm giving this talk now here. Exactly for that sort of questions. I'm done with just doing physics for the sake of physics. So I want to do stuff like this. How does this relate to physics? And how does physics learn from this, physics learn from that? And maybe it's just all the same thing.
Okay, interesting.
Can I, sorry, Pablo, just I want to add, Bob, what are you, do you have in mind something like that we're constructing the quantum reality and that the language is more fundamental? I don't know if you want to comment.
I mean, one thing is these circuits, I didn't say that, but this is not equivalent to language. This eliminates what I would call a lot of bureaucracy in language. For example, if you take different languages, then the diagrams I had at the beginning, they will look different for the reason that word orders are different in different languages. I mean, you can just take I love you and je t'aime. So the word orderings are already different. When you go to these circuits, all these differences vanish. They vanish. They're gone. So these circuits are much more universal than how we speak. So language-dependent stuff is gone, certain stylistic choices. And the reason there is that language wants to be two-dimensional. Meanings want to live in a two-dimensional space. Just like physics take place, and you know what I mean by two-dimensional. You've got the parallel and sequential dimensions. And language wants to live in two dimensions. And this reduced form of language, so it's not language itself. Language has a lot of unnecessary bureaucracies, which are basically the consequence that we as humans can only say one word after another. We can't say words in parallel and stuff like that and make like a two-dimensional Greek with words. We can't do that. But the meaning of language wants to be two-dimensional. And I think, and that again relates to Lucian's question, and these two dimensions, for me, they're exactly the same as the diagrams we use in categorical quantum mechanics. They're exactly the same. At that point, they're exactly the same thing. And in quantum mechanics, we talk about laboratory setups and quantum processes. Here, maybe we talk about like a lions chasing a giraffe or something like that. But ultimately, it's the same stuff. In one case, it's about physics. In the other case, about biology. But it's all about how stuff is interacting with each other. And the causal structures are there also immediately built in. Because when you have these diagrams, I don't know if people know that. I mean, you can look at this paper, but I'm going to say that people know causal structures from relativity and all that, like the causal structure, the partial order. These things are in a certain way equivalent to the causal structure. When you see a diagram, it's really the same thing as giving a partial order, causal structure, but in another way, they're much better. Because there's a lot of no-go theorems for partial orders. If you've got a partial order, you can't decorate it with these spiders. Impossible. And some other stuff. So these diagrams are sort of the fundamental structure of causality. Within this causal universe, you can have biology taking place, you can have physics processes taking place. So that's sort of the big picture, big universal picture, in the sense that I think this sort of unifying everything. And of course, when we speak, we talk about stuff out there. We talk about the physics. We talk about the biology. We talk about all these things. So in that sense, language encompasses it. But then again, going back to Lucian's previous question, language is pretty poor in its expressiveness of what we can actually describe. And that's why we need these other theories to actually enrich language.
Thank you very much, Bob. I yield to Pablo, who's been waiting.
Hi, Bob.
Hi.
So, so when your semantics for space is based on relations, then you get these neat causal structures like you had in page 85. But then if you go to Sean Tull's fuzzy version, I guess you get some kind of fuzzy causal relations. So something that looks like perhaps superpositions of page 85, I guess. I don't know. Generally speaking, my question is this. So I've always loved this diagrammatic approach to quantum mechanics, but on the other hand, I've always thought that this is talking about definite spacetimes and not quantum superpositions of spacetimes. But now you seem to develop a language that could be fuzzy and talk fuzzily about space and time. And so it's like you have diagrams about how diagrams ought to be branched somehow.
And that's it. I never thought of it like that. Now that there are things like the papers by Alex Kissinger where they use diagrams and they do the indefinite causal stuff too. So you know, Alex's Lick's paper with Sander Ireland, they do the indefinite stuff. But yeah, I mean, maybe these diagrams are all too rigid, or how would you say that? Too discrete. And one should think about like a fuzzy concept of diagram or something like that. But I mean, we have no. If you're going to do machine learning, you have no choice. You have to do it because otherwise you're not learning anything. You can't learn anything. You can't learn discrete stuff. You have to learn continuous stuff. I mean, it's an interesting idea that maybe this. I mean, it's fuzzy. Maybe they can be fully quantized. These diagrams. That could be really cool. I mean, the pity is they'll become a little bit harder to draw. They won't be that easy to draw anymore. But yeah, no. I mean, this work from Sean, it's not even on the archive. It's really very recent. But we're already using it because, like I said, we're trying to make a machine learn certain concepts like colors and stuff like that, entanglement. So we're already using that stuff now. This is really cool. We are, like the paper I was just presenting, we're actually already using it in actual practical experiments. That's really cool, actually. I mean, that doesn't work. That doesn't happen in academia.
Okay, cheers.
All right, I do not see any hands raised, but if there are more comments, please go ahead. You can also just unmute.
Yeah. Yeah, I'm just saying, since a year I'm on Twitter, so I post a lot of this stuff on Twitter.
Yeah, I have another question.
Who is that?
Deepak.
Yep, go Deepak.
So in quantum mechanics, we have something which we have the operator state duality, right?
Yeah.
So, but in this picture, I don't like see that it's not a.
Oh, it's here everywhere. I'll give you an example. It's everywhere here. This is it. This is exactly what I do. Next to goes from a state of two systems to an operator. So these cups and these caps, they allow you, these cups and these caps, they give you Choi-Jablonkovsky. So turning a state into a box or a box into a state, you just do with these cups and these caps, they witness Choi-Jablonkovsky.
Oh, I see. Right.
So you see it happening in front of you, sort of changing from state to, it's a picture.
Right, that's right. Thanks.
I mean, these pictures are useful just to do basic linear algebra. Things like that, like Choi-Jablonkovsky, transposition, they all have very simple diagrammatic incarnation. I mean, that goes back, that's Penrose, that's all Penrose.
Bob, forgive my ignorance. I know it's I'm trying to understand how I find very interesting somehow that you find natural language in quantum mechanics. I don't quite get it. So let me try to ask it this way. These diagrams this diagrammatic calculus that you have developed over all these years also describes classical physics, right? Is there something about the mapping of natural language on this diagrammatic calculus that says, you know, it works more like quantum mechanics than?
I mean, you have, it depends how much of the calculus you give. When we're talking about just these cups and these caps, then you're talking also, like I showed today, about the category of relations, just sets and relations. They have this structure. If you use the Cartesian product to compose them, they have this structure. You can take just classical probability theory. If you don't normalize it, you can say, okay, I take probability distributions and I ignore normalization. So they don't have to add up to 1. Then again, you get a category of exactly the same structure. you got the cups, you got the caps, and that's classical probability theory then, unnormalized. So you find these categories in a lot of places. It's not specifically quantum. They only become specifically quantum if you give enough additional structure, which in our case means spirals of two colors which interact in a certain way. Then you prove these theorems that whatever you can prove in Hilbert space, you can prove in these diagrams. If you don't take this full-blown structure, then they're actually very, for me, so the way to think about it is about these sort of categories is as follows. These are so typical structures like sets and functions. When in the case of sets and functions, when you describe a whole, then it's enough to describe the parts. This is where we say there's no entanglement possible. Like I take these two pens and I describe both by just describing this and describing that. So these categories are the complete opposite. This is situations where in order to describe the whole, it's not enough to know the parts. And this is kind of, we've written papers about that. This is kind of the most extreme situation. But think of this cup here, this cup on my slide, just this cup states. What this could represent, for example, is a twins. So what do twins mean? Twins mean that whatever feature one person of the twins has, the other one has two. But at the moment, I'm saying nothing more. You have no clue how each person in the twins looks like. You know nothing, but you do know that whatever one looks like, the other one looks exactly the same. So that's kind of what these sort of cup states are doing. So it's not particularly quantum. It's not particularly quantum. I can come up with lots of examples classically. It's not particularly quantum. This is it's just a very natural logical structure people never really thought about. And if you start thinking about it, a lot of things are much more naturally modeled with this sort of description than they are with your usual. You describe the whole by describing the parts. Because that actually rarely happens. That rarely happens. I mean, if you put two people together, you can't describe the whole by describing the parts because there's an interaction going on between these two people. It just happens everywhere. It just happens everywhere. Like our conversation we are having now is not just like by taking the properties of the individuals. It's something much more going on. And when you start thinking like that, like it's much more natural to have these non-Cartesian descriptions of things. Much more natural. People just didn't do it. People just didn't do it before, which is really weird. Quantum mechanics kind of, what quantum mechanics did is it enforced those. We couldn't get away with that anymore. That's, I think, what quantum mechanics did. Because in all of the situations we're trying to get away with not doing that, quantum mechanics said, yeah, sorry, you have to. And once you've done it, why not use it everywhere?
Yeah, okay. It's a nice way of putting it. Thank you. We can go. Well, there is a question by somebody that hasn't asked yet, Ranjit.
Let's go ahead.
We'll come back to Gislan. Ranjit?
Hello, am I audible? Hello, am I?
You seem to have an audio issue. Let's go to Gislan. Maybe you fix it in the meantime. Yep.
Thank you. So I had a follow-up question on, I think it's Roland Guichard who asked about the ambiguity in the language. And I'd like to look at a concrete example that you had on your slides with a pawn next to a king that a knight can capture. This one was ambiguous in the sense that the relative proposition could be also understand that the knight can capture the king. And I was just wondering, just also to get familiar with the framework, if you had to encode this alternative meaning with the knight that can capture the king rather than the pawn, how would it look like? How would you change the wires?
So an interesting thing about the category of relations is that it has ambiguity built in, of course. I mean, like the states in that category are subsets. So you basically have subsets of the union. So the union is like superposition in quantum mechanics. In the category of relation, the union corresponds to superposition. So you can basically superpose the different possibilities. So really working with relations, I said it before, is exactly the same as working with linear maps. It's supposed to be simpler, but we are so used to work with complex matrices that it's actually weird to work with relations. But basically, you can do everything you can do with matrices by just replacing numbers with zeros and one. So, and then the interesting thing is that in this case, like I was saying, you actually use superposition to be for ambiguity, if you want to. Now, if you want to have both superposition and ambiguity, then you have to do another, then you have to take something else. You can actually do a construction on the category of relations, which is exactly the same as the building of density matrices that gives you the two levels. So there is something in it. So you can actually go further to 3 levels. Nobody has ever used this for anything in the world, but you can do that too. I don't know what.
So my question was more about concretely for this change, if you swap, how you modify the wires, but maybe you could also take it offline. It was just to understand the intuition between how to connect them.
I just put off my slides so I could see people's faces. Because I was just talking to my own slides. So, but yeah, I mean, so I should share my slides again because right. Which one did you mean?
So the one with the complete, exactly this one. So what do you need to change here in the connections to make the knight capture the king and not the pawn? If you were to encode the alternate meaning, where do you need to modify the wires?
Wait, the pawn next to the
king, and it's a king that a knight can capture, not the pawn. Yeah, how do you modify the wires?
Okay, so people discuss whether this is actually truly ambiguous, and this has to do with like the priority you give to the head of the sentence. So the pawn. So well then in the pawn next to king, that a knight can capture. Let me see. So okay, but then the grammatical structure would change, huh?
Mm-hmm. Exactly. That's what I mean. And I was curious.
Okay. So then basically the king would go into the relative pronoun. Here, the relative pronoun now goes to next to. King would go into the relative pronoun. So the wire coming out of king goes straight to that.
Mm-hmm.
Goes straight to that. And then whatever came out of that is going to go to next to.
Ah, yes. Okay. Mm-hmm.
Well, good question. I had to use my brain.
That's what I wanted.
You were testing me.
No, I'm interested. I'm interested, and I like it. I like the framework.
Yeah. I mean, you know, this part, like this is. I mean, I hadn't even thought about it, but this is a nice example of where you get different parsers for different grammatical decompositions. And probably the parser would give the first one because kind of most likely, but one could mean the other one. This also says like the thing which happens, like if you take monoidal diagrams like these circuits, the diagrammatic representation, and you go to the symbolic representation as in category theory, then what you need to do is introduce a lot of brackets. Because a lot of that suddenly, because of forcing everything into a line, there's many ambiguous interpretations which you have to sort of get rid of by putting brackets. In this case, you could actually, and you see in this case, you could solve the problem by just putting brackets to make clear which interpretation you have, either brackets just around the first thing or brackets beginning before king and can capture. So the same thing, since language, like I said, wants to live in 2 dimensions, when you go to 1 dimension, you should actually introduce brackets. We actually should use brackets in language to avoid certain ambiguities. Of course, we don't do it.
Okay. If anyone has a last comment, otherwise we can thank Bob.
Hello, I hope I'm audible now. I'm Ranjit. I had raised hand. Okay.
We can hear you now. Yes. Go ahead.
Okay, good. Bob, so I want to make sure I'm understanding well. So when you say you can represent or encode ambiguous sentences via densities like density matrix in quantum mechanics. Typically, let's say an impure state in quantum mechanics can be purified, by various means, by additional of an ancillary, whatever. It can mean to say that there is some information that is lost in the local subsystem that we are talking about. So would it analogy readily extend to what you are trying to do here, representing ambiguous statements?
Yes. So there's a very clear interpretation to that. So basically, so in general, what you do is you build an entangled state, and then you sort of discard part of it, and that's sort of the way you sort of purify it. So here, basically, what this means, this adding of an extra system, is adding enough context so that there is no more ambiguity. That's
Yes,
literally what it means. That's literally so this purification has a very clear interpretation. It means adding enough context so that the ambiguity goes away.
Well, usually in text, the way you add more context is write more text. So in quantum mechanics, we can say the way you add more context in your science is by attaching more ancilla, whatever.
Yeah.
Probably so that works fine. Then I am curious, the vocabulary or the baggage that is required to describe physical processes, let's say just quantum mechanics, would that be almost equal to the vocabulary that's required to represent any possible phenomena of world, like any possible linguistic sentence, or is it just a smaller subset? I'm just curious from your way of representing this sentences of a language. How much baggage would it require to describe quantum processes, let's say?
So are you trying to say, like, how much more structure do I need to add to specifically get quantum?
Or maybe how much you need to remove? I mean, are all phenomenon of word a superset of quantum phenomena, or are they just a subset of this quantum world? In some sense, the baggage to describe whether the baggage to describe quantum processes is something more than the baggage to describe any other process in the world,
So I mean, if you're strictly talking about the diagrams, like in quantum mechanics, we know what we're going for. We know what we want to describe, and so there you can say, okay, we add this amount of structure to the diagrams, and we exactly get quantum mechanics. For here it's kind of much more difficult to know what you're shooting for, and basically what you do then is you build a dictionary of words represented in some mathematical way. So you're adding a lot of data by hand, and that's not structural. That's sort of I mean, we're trying to improve this. Exactly what I've been talking about today is just trying to improve and getting a better structural understanding. But it's kind of related to what Lucian was asking too. Like it's much harder to know here what you're shooting for, what your goal is. And I mean, in one way, you could say anything within quantum mechanics should be part of language because we can describe it. But then you have to sort of bring in all the mathematical structure of quantum mechanics into language too. And then it's a difficult one. It's a difficult one. And one can think about it in many different ways.
Probably I can ask it in another way through an example. Like you used the example of word hates. Alice hates Bob, or something like that.
Yeah.
So does the same representation method work equally well for sentences involving knowledge representation? Like Alice knows Bob, or Alice knows that Bob is not going to like it, or Alice knows that Bob has pin Z up, when he measures the spin in his laboratory. These kind of sentences. Would they be represented almost the same way like Alice Head?
Okay, I get it. So you're talking, suppose you take sentences about physics, then your model of meaning needs to account for all of physics, needs to allow the representation of all of physics. So
okay.
your model of physics meaning should include quantum theory to be able to represent all the meanings of quantum systems. If you're talking about relativity, your model of meaning should include the relativity theory in order to account for all the meanings of relativity.
In a way, I thought that's what was Lucian Hardy was asking about. I mean, can you somehow, get these systems to talk about physics or quantum mechanics in this fashion that they can describe experiments accurately, etc. Well, that's just.
I mean, it's a difficult question. I mean, like I said to Lucian, I'm still thinking about these things.
Okay.
It's not.
Well,
Okay.
it was really interesting. Thank you.
Thank you.
Is there any final comment, Lucian? Do you want to say something?
Oh, I think so. Bob started to talk about sort of where this. I think almost a philosophical question, how you understand physics, whether physics is a fundamental theory that's somehow deeper than language, or is the relationship the other way around? Would you elaborate on that? I think you were alluding to that previously.
Yeah, I mean, this kind of connected to what I was trying to say now. Like, I mean, you know, there's been this attempt like long ago by von Neumann. I mean, the Greeks, they thought that everything you could say about the world, you use propositional logic. That's Aristotle. Then von Neumann thought, okay, we need to extend this a little bit, and then we can also say everything about quantum mechanics using quantum logic. Obviously, this was, but both programs were complete failures. You know, logic as we use it and as we speak it has very little to do with Aristotle and maths things about logic, and also the quantum logic was an even bigger disaster. So maybe that's the best analogy. What I see here is an attempt to do something like logic, a structure that would encompass physics and everything else. And language, the way I think about language is just a reflection of that. It's a reflection of that. We've a lot of sort of bugs, and the bugs come from the fact that you have to stick it in a line instead of into a picture. So that language is bugged as hell. I mean, we haven't got this paper out. We're soon going to put a big paper out about like how messed up language is because our stupid ability to only speak word after word and listen word after word. But yeah, so that's my current view. So there is a logic, there is a new kind of logic, which is much richer than anything people have called logic, which is encoded into the circuits or something like that, which very much looks like causal structure again. It's the same story, which encompasses physics, which encompasses pretty much everything going on in the world. That's my current view. That's my current view. Language is sort of a reflection of that. And
okay, that's great. I like that.
Although language to say something more, to an incredible extent, language is very much focused on physical space around us. Either explicitly, like in prepositions, or metaphorically. A lot of what we say is just all about physical space around us. I mean, it's not a surprise. Probably, I mean, maybe somebody knows more about me. When did people start speaking? When did they start speaking? Probably when together they were trying to go for a mammoth. You know, you have to coordinate. You can't just do, you have to speak to each other if you want to take down such a big beast. And this is completely spatial sort of action. So I assume that a lot of there is something better to understand about this connection between language and space than what I presented today. There's something deeper to understand there, I think. I mean, then the more interesting question is how to talk to aliens. So how are we going to speak to aliens? I mean, it may sound stupid, but in all these different levels I've been speaking about, like possibly aliens can speak 2 dimensions. So how stupid language, word after word, probably not. There's actually not a bad. There's actually this movie with the aliens doing weird 2-dimensional circle stuff. I don't know what the name of this stupid movie, but at least that idea of 2-dimensionality was a good one. But so are aliens as much embedded in physical space as we are? Maybe not. In that case, their language will be again a completely different thing, because I think our language is so much entered onto physical space. And so, I mean, it's an interesting question to think, like how much you need to break your structure down to actually find a point of common understanding. So a lot of what you're asking actually is part of the thought process of just a question how to speak to aliens. Because you can think of an alien as another physical being which may have completely different senses and properties, and henceforth the relation for the alien word to their language would be completely different than our relation to between language and the physical world, because they might have a completely different perception of the physical world. So it sounds like a stupid question, but it's actually a very sort of inspiring one, at least for me, when you start from this context.
Yeah, thanks.
Thank you. Thank you. The good part was you were saving it for last. Okay, maybe we can wrap up. It's been 2 hours. It was fantastic talk, very exciting. Thank you very much, Bob, for your time, and thank you everybody else for the interesting comments and questions. And
thanks for listening. Good to see some of you again after a long time.
Yes, hope we meet in person soon too, somewhere. And
but you know, Marius, we are working with Vienna. We're working with Philip Walter.
Ah, really?
Yeah, we're doing all this language stuff now. I mean, we're trying different hardware, so we're actually doing this language stuff on optical devices with Philip.
Oh, I didn't know that.
So I'll probably pop in at some point there.
Yeah, it would be fantastic.
I was planning to come over we started this just before COVID, and I almost booked my tickets to Vienna, and then something happened. Don't ask GPT-3 because it doesn't know.
Okay. I hope we see you soon at Vienna.
Okay, bye everybody.
Bye everybody. See you next time. Thank you, Bob.
Bye.
Cheers.